Hello, 30-1s. Today, we're going to look at the remainder theorem. What I want you thinking as you're going through these lessons in polynomials, one of your main goals is to be able to graph a polynomial that's not in factored form without using our calculator. What we saw in previous videos was how to use division, long or synthetic, to help us find the factors so that we can graph. Today, what we're going to look at with the remainder theorem is a bit of a shortcut to using long division and synthetic division to help kick off the process here. Let me show you what I mean. Okay, in the last lesson, we looked at a polynomial like this, and we did some long division and synthetic division. Let's take a look at a new polynomial. So let's consider a new polynomial. We'll call it p at x, and we will say p at x is x cubed plus 4x squared plus x minus 6. Now, what we want to do here is we want to factor this thing. But before I factor it, let's go ahead and let's just graph this thing in our graphing calculator. Let's take a peek. So when we graph this, what we're going to see is we will have an x-intercept at -3. We will have an x-intercept at -1. And we'll have an x-intercept at +1 and a y-intercept down here at -6. And if I graph this, it looks more or less just like that. Okay, so there's p at x. Now, just by looking at the x-intercepts, I actually, again, know what the factors are. If I look at my x-intercepts, I have an x-intercept at -3. That's my factor x plus 3. X-intercept of -1, factor x plus 1. X-intercept at 1, factor of x minus 1. There it is. There's p at x, factored. But I did it by looking at the graph. How do I find these points without being on the graph or not having the graph in front of me? Well, we could long divide or synthetic divide, or we're going to look at something here called the remainder theorem. Here's how I want to think of this. Let's consider this x-intercept right here. This x-intercept, what this is telling us is it's this coordinate pair, 1, 0. But let's look at what happens here. This is x is equal to 1. And it says y is equal to 0. So let's go to our polynomial here and see what happens. I'm going to let x be 1. I'm going to substitute that in. 1 cubed plus 4 multiplied by 1 squared plus 1 minus 6. What does that equal? 1 plus 4 plus 1 minus 6. P at 1 is equal to 0. Oh, look at this. Here's my x value. Here's my y value. So by subbing in values for x, the output that we get out of our polynomial is our y. Well, we just found a coordinate pair on our graph. Easy as that. Okay, now there's an infinite amount of coordinate pairs on this graph, but I'm going to label another point here. This point up here is the point 2, 20. All right, let's see if this works again. So I go to my polynomial, p at x, and I'm going to substitute in my x value of 2. Look what happens. 2 cubed plus 4 times 2 squared plus 2 minus 6. P at 2 is equal to P at 2 is equal to 24, 26, 20. Hey, look at, there's that y value again. This is the coordinate pair 2, 20. What we just did right here is we actually just used something known as the remainder theorem. So here's what the remainder theorem tells us. We have a polynomial, p at x. When we sub a value in for p at x, whatever we get as an output is the corresponding y value on our graph. What the remainder theorem says is this. We're going to sub in a value a. I don't know why someone chose a, but that's how they usually write it. We're going to get a number that's not 0. So what this tells us is two things. X minus a is not a factor of our polynomial, is not a factor of p at x, because we don't get it equal to 0. But what it does tell us is a coordinate pair. It tells us whatever value that comes out of this thing, a and p at a, which is the y value, is a coordinate pair on our graph. That's it, my friends. So really what the remainder theorem is telling us is sub in a value. If we get a number that's not 0, it's not an x-intercept. It's another point on our graph. That's all it's saying to you. Guess what? The next lesson is going to talk about the factor theorem. And the factor theorem is the exact same, but we want our value when we sub in to equal 0. That is all it's trying to tell us. So let's try another one of these. Pick a polynomial. P at x is equal to, I don't know, let's just keep it easy, x squared plus 5x plus 6. So a nice quadratic from grade 11. I say we're going to divide this polynomial by x plus 2. Now, we could do long division, we could do synthetic division, but I'm going to instead use the remainder theorem. What the remainder theorem says is I'm going to let x equal -2. So p at -2. I sub this value into my function. If it's equal to 0, it's a factor. If it's not equal to 0, we have a remainder, and we know a coordinate pair on our graph that's not an x-intercept. So p at -2 ends up being, well, look at this. It's 0. So guess what we just found? Therefore, we have an x-intercept at -2, 0, and therefore x plus 2 is a factor of p at x. There it is. So look at that one, actually ended up giving us a factor. So that's really the factor theorem. Well, I don't know why they ever decided to give these two different names. The factor theorem and the remainder theorem are the exact same. Try it one more time. I'm going to use the exact same polynomial. So here we go. P at x, x squared plus 5x plus 6. But this time I'm going to say we're going to divide by x minus 4. So I'm going to use the factor theorem and the remainder theorem. I'm going to let x equal 4. So p at 4 is equal to 4 squared plus 5 times 4 plus 6. P at 4 is equal to 16 plus 20 plus 6. P at 4 is equal to, what is that, 42. So this is not 0, right? 42 is clearly not 0. It's not 0. So x minus 4 is not a factor of p at x. But what is it? I'm just not going to ignore it. I want x-intercepts. I want factors. But okay, it's not a factor. What is it? What this tells us then is we have a coordinate pair. The point 4, 42 is on the graph of p at x. That's it, my friends. That's the remainder theorem. And like we've seen, the factor theorem is really the exact same. Do I get a 0 when I sub in a number? Do I not get a 0 when I sub in a number? There's your factor theorem and remainder theorem. Easy. Okay, last thing we need to talk about then is how do I know what to divide by? Right? How do I know what to divide by? Well, if the question tells me, that's easy. But what if the question doesn't tell me? So say I've got a polynomial. P at x is equal to, I don't know. Let's go to x cubed plus 2x squared minus 6x plus 8. Okay, and the question said, let's find some factors or some x-intercepts of this polynomial. Okay, here's how you try. What am I going to try to divide by? The question doesn't tell me. So what you're going to do is you're actually going to look at your constant term. And we're going to list all of the factors of 8. The factors of 8 are positive negative 1, positive negative 2, positive negative 4, positive negative 8. What these are your possible or potential zeros. These are the things that could potentially make p at x completely equal to 0. Okay, so now here's what we're going to try. Let's just pick one. P at 1. I sub it in. And I see what I get. Well, p at 1, 1 plus 2 minus 6 plus 8. Well, that's 3, that's 11, that's 5. Well, that's the point 1 comma 5, but it's not an x-intercept, right? I'm trying to factor this thing. So the way this works is you need to go through these 8 different possible zeros and say, okay, which one of these could give me an x-intercept when y is 0? Well, unfortunately, my first guess was a bust. I didn't get a factor. So back to the drawing board. I'm going to choose another point, or another possible 0, I should say. This time, I'm going to choose -4. I'm going to let x equal -4. I see that one right there. Okay, well, I'm going to sub that in. That'll end up being -64 plus 2 times 16. And I'm running out of room here. I apologize. So I'm just going to write it downwards like this. And guess what we end up getting? -64 plus 32 plus 24 plus 8. Well, guess what? That's 0. So what does that tell me? Therefore, x plus 4 is a factor of p at x. Also, we have an x-intercept at -4, 0. So that's the factor theorem. I got a 0. It's a factor. Over here, I got anything but a 0, so it's a remainder. So I'm hoping you're seeing how these two things, even though they have different names, are the exact same. Now, wait a minute. You're telling me I might have had to have searched through 8 different possible factors before I got this one right. Technically, yes. However, let's be smart about this. You have a graphing calculator. So maybe, just maybe, it's a smart thing to graph this first and see what your x-intercepts are, and then show me that it is indeed a factor. Just a little hint for you that you should do. Okay, this here, listing the possible factors, is known as the integral zero theorem. All right. So, friends, that's it for the remainder theorem. The remainder theorem simply says sub in a value for x. For some reason, when you're looking at this theorem, they usually say, let's make that value a. If p at a is not equal to 0, we have a remainder. And what I want you to think is this is a point on our graph. It's the point a comma p at a. That's it. So it's a little bit quicker than long dividing or synthetic dividing, and it definitely comes in handy. Okay, hope that helped. See you next time.